How do you determine what is occurring when two solutions are mixed? How do you calculate the mass of the precipitate and all of the ions present in that solution? Let's cook. So here's our situation. What if we mix 100 mils of a 0.2 molar silver nitrate solution with 150 mils of a 0.1 molar sodium carbonate solution? We're going to do 4 things, and maybe your problem that you're being asked doesn't ask for these 4, so you can fast forward if you need to. We're going to identify the reaction. We're going to identify the precipitate, which go hand in hand. We're going to calculate the mass of the precipitate. And then the hardest and most challenging part is we're going to calculate the final concentration of all the ions present in the solution. So first, let's take a look at what is the reaction. So knowing polyatomic ions and knowing charges of ions are really important. So if I take a look at this and I have my problem, I like to work within the problem first. So I have silver, and I know that silver has a +1 charge. I know that nitrate is a polyatomic ion, and that's NO3-. All right, I have sodium carbonate. Sodium is Na, and it's an alkali metal, so that is a +1. And carbonate is CO3 2-. Well, why does that matter, and why is that so important? Because at the end of the day, it's all about crisscrossing. So we're going to have different kinds of problems. We need to combine these two, and we need to combine these two, which is going to create a double replacement reaction. So the first thing we're going to talk about is a molecular equation. So I'm going to place the silver with the nitrate. And because it is a +1 and a -1 charge, those stay. Those are 1-to-1 ratios, so it's just AgNO3. Next, I'm going to place the Na with the carbonate. And because I have a +1 and a -2, those charges in some ways need to cross. We need 2 NAs for every 1 CO3 to balance those charges. And that is a classic double replacement reaction. So then what occurs? The cations and the anions, in essence, need to switch places. One of them does. So either the silver and the sodium, or the nitrate and the carbonate. So let's make this simple, and let's keep the silver here. So now who's its new partner? Instead of a nitrate, it's now with the carbonate. And then that means that the sodium is now with the nitrate. The beauty of this is that the charges stay the same. So I have a +1 and a -2 and a +1 and a -1. So what would be the final charges or formulas? The 2, in theory, comes down here. Okay, knowing solubility rules is really important. I know that all nitrates are soluble, so that is AQ. That's going to be a big deal in a minute. And I know that all alkali metals are soluble, so this is going to be AQ. Okay, so I come over here, what I just said, all alkali metals and all nitrates are soluble. So because of that, out of process of elimination, I know this is going to be my precipitate, the silver carbonate. So in theory, this is the solid. It's actually a pale yellow, not a white. But I want a net ionic equation. So if I take this, and I'm just going to bring this up a little bit. In chemistry, we know that anything that's aqueous actually turns into ions. Before we do that, we should balance this quickly. So I have 2 NAs, I have 1 Na, so I need 2 of those. I have 2 NO3s, so I need 2 NO3s. Because of that, the Ag is 2. Look at that, it's balanced. So anything that is an ion comes from an aqueous solution. So what I'm going to do is I'm going to turn these back into their ions. We'll talk about how to balance this in a second. A solid stays together. And once again, ions break apart. So it's as simple as looking at the numbers. So there's 2 AgNO3s and 2 NO3s. So I put a 2 and a 2. There's 2 Na right there. And there's a 2 Na and a 2 NO3. So I need a 2 here and a 2 there. Sorry, that's a little cramped. So what occurs? Well, what occurs is that there are ions that are exactly the same on both sides. And these are called spectator ions. What do spectators do? They watch. So ultimately, my net ionic equation are the ions that make the solid, which looks like this. So that is my net ionic equation. It is very messy, I understand that, but we'll work on getting through that. So what is my precipitate? My precipitate is the silver carbonate. Right? Identify the precipitate, silver carbonate. Okay, the next step. What if you're asked to calculate the mass of the precipitate? So the overall equation or the net ionic equation can be used, and I know there's more than one way to do this, but we're just going to do it this way. So I'm going to use the overall equation, which is right here. My silver nitrate plus my sodium carbonate produces my precipitate. So I like to organize all of my information. So I have 100 mils of a 0.2 molar solution, and I have 150 mils of 0.1 molar solution. This is what's coming to the table. And what I want is grams of this. So what do I do with these numbers? Well, these numbers are screaming molarity. The molarity equals moles over liters. So if I place the molarity here and I place my volume, which I need to change to liters, I can find out the moles, or the amount of stuff that I have of each ion or each reactant. Okay, so we're going to kind of try to keep this organized. So I'm going to talk about this in terms of the entire compound. So here's my silver nitrate. So I have 0.2, and I know that this can be set up in a couple different ways, but this way I never make a mistake on maybe where I'm setting this up. So 100 milliliters is now 0.1 liters. Now I have moles, so 0.1 times 0.2 is 0.02. I'm trying to keep some sig figs here. So that's of AgNO3. Okay. And then if I talk about the sodium carbonate that's brought to the table, I have 0.1 molar, and that's moles, and then I have 150 milliliters of it. So that's 0.0150 moles of Na2CO3. So what do I need? Guys, I need to find the limiting reactant. Which one of these is going to run out? So for every two of these, I need one of these. So you might be able to see that right now. I'm going to say it. I need double of this, then this. So maybe you can already see, do I have double of that, then this? It doesn't look like it. I would need 0.03 to be double that, right? So I need to times this by 2. If you're not sure, you can also do a little quick stoichiometry and compare it to the other one. So for every 2 moles of AgNO3, I want to get rid of the unit, so that's why this one has to go down here. I have 1 mole of the Na2CO3. See, the 1 goes here, 2 goes there. So if I cut that in half, what it basically tells me is that I need 0.1 moles of the Na2CO3 needed. And if I take a look, needed versus this, I have more than I need. So the the sodium carbonate is in excess. Once that's in excess, that means that the other item is the limiting reactant. So this is my limiting reactant, the silver nitrate. So now what I can do is finish this doing just a little stoichiometry. If you need help with stoichiometry, find my videos on stoichiometry. So I take the amount that is present of the silver nitrate. I'm going from moles to grams, so that's 2 more steps. So first I do the mole ratio. So I do 2 moles of the AgNO3. I'm heading now to the precipitate. So there's 1 of those for every 2 of these. 1 mole of Ag2CO3. Okay. Immediately now I want to know what 1 mole of Ag2CO3 is with a molar mass. So if you take 2 silvers, a carbon, and 3 oxygens, you get 275.8 grams of silver carbonate. Multiply that out, and the final number, and I will write it right in the actual precipitate, is 2.76 grams of Ag2CO3. That is the mass of the precipitate. Okay. The final step, which is by far the most difficult, once again does require the overall equation because it's just more helpful. So if I am making the solid, in a lot of chemistry problems, it's asked to label a solution. I know for a fact that this is my solid. Okay. Well, if that's the case, this is what I know was brought to the table. So what I want to know is what ions. If each one of these is an ion, what's present? So let's make a list. I have silver ions. Reminder, brackets are concentration. I have nitrate ions. I have sodium ions. And I have carbonate ions. So notice how I did that. I just grabbed each one and I just listed it. I haven't even thought of anything yet. Now let me make life easier for you. These two are spectator ions. Why? Because they are not involved in the precipitate. So these are going to be unchanged. These two are tricky. One of them does not exist at all. The reason why is as these are coming together and making my solid, one of them eventually has to run out. So which one of these is part of the limiting reactant? Well, we just learned that silver nitrate is a limiting reactant. So this right here is my limiting reactant. This is an excess. So this is 0 molar. Now, if you continue in chemistry, there's a thing called a KSP, and this will technically increase, but for all intents and purposes, that's a 0. So let's talk about the other one, the excess. Actually, let's work the way down. So nitrate, nothing's changed with this. So what came from this? Well, if I go back, the nitrate from our previous part, the nitrate, this is all of the moles that contribute to the nitrate, or from the nitrate. So I have 0.02 moles of nitrate. So if I have 0.02 moles of nitrate, okay, then I want to put it in the total solution. Remember, there's two solutions moving in here. So what I need here, and maybe the trickiest part of all this, is I need the total volume. I'm mixing two solutions. So I had a 100 mil and I had a 150 mil solution. And then I'm just going to label it liters. So I have 0.0800 molar. Okay. Sodium. If I take a look at my sodium, I had 0.01 moles of my sodium carbonate. So I have 0.015 moles of my sodium. But there are two of them. So there's only one of these. This does not matter. So I need to multiply that by 2. And then I still put that over the total volume. And I get 0.120 molar. And finally, the most tricky one. I started with 0.015 moles of carbonate. But this is part of the precipitate. So as it's being used, it is getting consumed. So what was being consumed? You've actually done the work. This is how much was needed. So if that's how much was needed, and this is how much I started, I have both these together. Start my initial, my final. So I'm going to subtract what would be consumed if all of the silver was used up. So if I were going to zoom in on this, this is my initial, and this is my consumed. And then I put that over my overall volume. Once again, it's all the same volumes. And those are my final concentrations. Now, a little bonus. What if you were asked to place the ions into this solution? Well, the simplest way to do that is to divide each number over the smallest number. So this is the smallest number. So if I divide 0.12 divided by 0.05, I get 6. So that means there would be roughly 6 of these Na pluses. So 1, 2, 3, 4. That's a lot. 5. We'll sneak one in here. 6. Let's take a look at the next one. If I take 0.08 and I divide it over 0.02, that's 4. So I'd have 4 NO3s. 1, 2, 3, 4. Because I'm dividing them over, that means there'd only be one CO2 minus. I know that's a little congested, a little ugly, but that would be the ratio. We learn how to take a reaction into a net ionic equation. We learn how to identify and calculate the mass of a precipitate. And we learn how to calculate all the final concentrations of all the ions. Wow, keep cooking.